Okay. Hi. We're gonna discuss about the course introduction on control technique today. Let me just share the file. Okay. So we're going to discuss about the introduction on control technique. What is it actually, and then how can we apply that in our study or even in our field of work. So what is control technique? So it is simply a study about how to control a certain process. Yeah, so it does apply to many others field on top of engineering. So it can be as simple as management process or budgeting or costing process. So we need to control the budget. That's why they call it sometimes budget control. So to make sure that it's not just that it is not used overly, but also that it is used, that it's not used too little. So actually, when you budget something, then you need to use them properly. And then general management process as well as engineering or automation process. So this is what control technique will be relating to. So if I just get the general definition of control technique or control engineering or control system engineering is an engineering discipline that deals with control systems. Yeah. So we are applying the control theory to design equipment and system with desired behaviors. So in a control environment, so it means that you want your system to behave in a certain way that you desire. So that even though there are some disturbance, some noise, some other uncalculated event that occur within the control environment, that we can make sure that it will behave accordingly to what we have desired. So, automatic control has played a vital role in the advance of engineering and science. While control theory has been extremely important in the development of space vehicle systems. So, when the outer space, we send a vehicle, drive automatic guided vehicle, also even missile guidance systems. That's also having a control system. You see, like missiles can be directed to a certain point. Despite of disturbance, it will just go to the targeted point. Yeah, a robotic system. So this has also become an integral part of modern manufacturing and industrial processes. So it has been implemented a lot. Yeah, in the last 50 to 70 years, control theory has also been introduced into a wide variety of application. So it is not just engineering. So the greatest impact has probably been in medicine. Yeah, so medicine, with the body now being regarded as a function of a complex dynamic control. Yeah, so other application can be also economics, sociology, and management. We can also design the pattern of urbanization, people that move from villages to city, and then how the pattern that we can control, how the multiplication of the number of people within a certain region. Then we can also see the pattern, and then probably the government or the local government can also do something about it. Yeah. So control engineering, control technique, control system is applied to many disciplines in life. But when we are talking about a certain engineering, control system is an arrangement of physical components connected or related in such a manner in order to command, to direct, or to regulate itself. Sometimes, most of the time, automatically itself, or also controlling, regulating another system. Yeah, so that's the I would say the more engineering control system definition of that. And each control system has input and output. So it's like a black box, yeah, within inside it as a control. system, control algorithm, and then when we have input, then these things will somehow outputting something. Yeah, there must be an output. If there is an output, then there's no point that you can control it. Yeah, so each control system has input and output. So let's look at the input definition. Yeah, input is the stimulus or excitation applied to a control system from external source. Yeah, usually this is to produce something that we desire, something that we're looking forward to. So something that we desire. Yeah. So that's what the point of giving some input. Uh, and the output is the actual response upon feeding the input. Yeah. So after we feed the input, whatever the output, the actual response of that, we call it an output. It may or may not be equal to the specified response implied by the input. So it can be, yeah, it depends on the system. It depends on the control system. So how we can, that's why we study control system, control technique, so that we can somehow assign a control algorithm so that when a certain input is being fed into the system, into the control system, then the output can be managed or engineered to be specified into a certain range or certain terms, yeah, by the designer, of course. So control system looks like this. So we have like a box here. Inside is a control system, and the input will comes from one side, and the output comes out from the other side. Yeah. So what are the control system applications? So this is the, of course, with regards to analysis and design of goal-oriented system. So there is a goal, there is an achievement, there is a target, there's an aim. So this is talking about also automation, making it automatic. So when there's something comes, there is also there's already an algorithm there, control algorithm, that will be outputting something, yeah, automatically. Yeah. So control system play an important role in the development and advancement of modern civilization and technology. Yeah. So even nowadays, everything is being automated. Even when you want to dial a phone, calling somebody, you don't need to dial using your hands anymore. You just call the name, maybe the name. I want to call such and such, and then it just ring. There is a voice recognition, and then there is this machine learning, or there is this already program system that will do it for us. So this is talking about automatic system. So this kind of thing, and also control system, is actually improve our day-to-day activities in such a way. So there are many of these now, and the use are varying from generation of energy, electricity, transmission of that energy, communication, transportation, industrial processes, power system, micro electromechanical system, MEMS, even nanotechnology now, robotics, consumer electronics, economy, biology, medicine, and many things. Let's just look at some typical examples of control system. Yeah. So if you look at this is actually a diagram or picture, a drawing of a toilet tank. You see, automatic control that is fully mechanics was invented long time ago, over 200 years ago, 1775. I think it was by Abraham Cummings. The name was patented that. Yeah, had the patent for that. And this is actually, when probably realizing on that, when at home, our toilet still works in similar way. So when you flush the toilet, you don't fill the water by yourself into the tank, but it fills itself up until to a certain position and then stop. So it will be ready for you to flush it again. Yeah, that is actually an automatic filling tank. So what happened here? Let me just get my laser pointer. So this is like this is the handle. that a human will just push or pull, whichever you are looking at it from, uh, and then it will just take off this flush valve. It is like opening the gate. It's like the gate opening for the water to be flushed down, to be let go downwards here. So when you flush it, and then the water will go down, and then there is this float ball, because the water has gone down, has been used up. This float will also go down because it is up there due to the water. So when it is down there, somehow in here there is an inlet valve. The inlet valve, when it is in this position right now, it is stopping the water from the supply line here to the tank. This is the filler tube, the outlet from this side. So when the water is flushed down, so there's the water has gone down, so it is like draining it down. The float will go down. It opens the inlet valve, and as long as the float is down here, for example, then the water will be filled into this tank. And then as it is being filled, the water will rise again, and the float will rise again, and at the same time it is closing the I would say the amount of is limiting, starting to limit the amount of water that coming from the inlet tube into the tank, until it reach a certain position that it is actually stopping the water to come in, and that's it. The water is filled, the tank is filled, and it is ready to be flushed again. So this is actually what we call a full mechanic control, automatic control. Yeah. What else? What next? Next is James Watt speed governor. I think this is also around the same times when steam engine was invented. Yeah. So James Watt, when invented that, he created what we call as the speed governor. So this is to govern the speed engine. Yeah. So what it does is, when they invented the steam engine, so the steam is actually drive a turbine. So it is moving a turbine, so it is driving what we call an engine. Yeah. So in turn, this engine will do something to a load, whether rotating conveyor belt in manufacturing, or driving whatever it may be. Yeah, we're not talking about that. So this engine will be moving. So sometimes because this engine is used to drive, to transport, to rotate, or to move something in a certain speed, so we want the speed to be constant. So when we want the speed to be constant, then James Watt invented what we call as the speed governor. This is already also about 200 years ago, I think. So this engine is coupled with some gear here to a speed governor there. So this is some kind of pendulum is put on this. This is rotating. Yeah, this is rotating, horizontally like that. Yeah, pivoted on here, so it is rotating like that. So it is rotating in a certain speed. So when the steam comes here, and then the engine move by gear connection, this also will move, of course. And this, like an inverted pendulum, when it is rotating, there is a centrifugal force that it will fly, basically going around, and then lift it up like that. As this pendulum will be lifted up, it somehow move this. Yeah, somehow move this, which will close and open the pilot valve there. Yeah. So for example, we want we want to make the engine to be at certain speed, and this one will be designed that it will move in a certain speed that will make this pilot valve to be closed at this point. So if there are some disturbance that makes this is slower, yeah, so this pendulum will go down. As this pendulum will go down, this pilot valve somehow will be open. This is going down, and then there is this oil will be coming here and push this down, so it is opening the control valve even more. So if this slowing down, opening the valve, causing the valve to be open more, and it will speed up the engine and it will go back to its original speed. Vice versa, if this is too fast and this one will go up, because this pendulum will go up also, this one will go up, and then the oil will go down here and push it up. So it will pull this control valve, closing it a bit more. So the engine will slow down by itself. So this is like automatic speed governor. Yeah, it has been done quite a while ago. What else? Yeah. So maybe this is just a simple graph or schematic diagram of temperature control of an electric furnace. Yeah. So this is the furnace. Yeah. Thermometer, and this thermometer is analog sensor, and then there is an analog to digital converter. Some of you probably have studied that, and then there is an interface going to a controller. Yeah. And then again, from the controller, it can be PC, PLC, whatever it may be, microcontroller going to interface, and then there is an amplifier relay to also control the heater there. Yeah. So we want to make sure that the temperature is maintained at a certain point. So that's why there is a sensor there and there's a controller here. So when the temperature is being measured is lower than expected, then the controller will tell the amplifier to heat up. Yeah. Or vice versa, if the thermometer says the temperature is already too high, then it sends a message to the controller. Controller will tell the amplifier to slow down a bit. Yeah. And then to cool down a bit. Yeah. So what else? Examples. Oh yeah, biological system reaching for an object. Actually, when we are when I want to reach something, then my eyes become my sensors, and it tells my brain or where the object is, and then the brain will tell my arm to go over there. In a slow motion, my hand will be moving while I'm watching the object. So it's like a continuous information. You are not reaching there yet, continuing. So I keep moving my arm until I reach it. So that's also an example of a control technique. What else? So object position is the input and hand position is the output. This is the actuator. This is the input from the sensors, my eyes. And also this is magnetic levitation transport. Magnetic levitation transport, you know that the very high speed train, that it can be reaching a very high speed because there is no friction, or very minimal friction because there is no contact between the train and the rail. Yeah. So what is the control in here? We are doing the transport rail spacing. That's the output. So voltage is given and control system will make sure of that. Yeah. What else? Another example is aircraft control system. Pitch angle, roll angle, and the yaw angle. We just control it through the control system and all that. Let me just show you. I took it from the YouTube. This is control of ball and plate. Yeah. So just have a look at this. This is actually 6 degrees of freedom. Yeah. Look at that. One of our students have done some experiment of this. Of course, he just did it for 2 degrees of freedom, but it was successful also. But it was quite a while ago. I think already almost 8 years ago. I think so. I didn't. We didn't have any documentation of the camera of that. But this is the how we can actually control the ball to be always in the middle, the center of the plate. So when we do a disturbance to it, then it should be coming back. And this is just controlling using a joystick. Yeah. So joystick means like we are changing the the center point. We are changing the equilibrium point. So if we change it to the middle or to the left, so when we are setting that using the joystick, then whatever the disturbance comes in, then it will try to make the ball to stay in that position always. Yeah. Okay. Just a simple example of control system. This is using a simple PID also. Next is so control ball and plate. Oh, hang on. What happened? All right. Let me just go to a bit of a mechanism that happens. So I just want to give the idea that in control mechanism, we need to understand there is the physical term and there is this electrical term, physical entity and electrical entity. So in all, in most, if not all, yeah, engineering control, there are this mechanism, something that take place, some purpose of using that. So we are driving something, so there is an actuator, and we want to know the actuator has done something, whether it is increasing temperature, pressure, or just position changing. Then we need a sensor to sense that. Yeah. So and then there must be some kind of brain to actually coordinate all of this. Just like my example before, that I want to grab an object. So my eyes is my sensor, the actuator is my hand. So grabbing the object is the mechanism. So my brain is actually somehow the device that control connects them all. Yeah. So if you look at this, okay, so mechanism on the top there, I put a line here that separates the physical signal and electrical signal. Yeah. So let's say a smart home. Yeah, I'm putting this example, a smart home. I didn't really think that I put it there, but yeah, as I put smart home, maybe we can make an example of motion detector. Yeah, so motion detector. So let's say you don't need to unlock your door, you just get in front of the door will be opened by itself. So basically there should be a sensor, yeah, a sensor, whatever sensor you can use, proximity sensor, facial recognition sensor, or whatever it is, and that's actually capturing the physical signal and then transform it into electrical signal, and then it will tell the, maybe you're using a PC or PLC or microcontroller, it will determine it is the right person on the door to be allowed to come in. And then if it is yes, then the brain will tell the actuators to open the door. Yeah. And then that's it. So this is the mechanism like that. Yeah. So this is actually what I just try to make a simple example that can be understood easily. So, but we need to understand that there are two types of signal here. There is a physical signal and electrical signal. Every time we want to get the information, it is a transformation from physical signal into electrical signal, electronic signal. Every time you want to drive something, drive a motor, drive a pneumatic solenoid or whatever it may be, then usually it is a transformation from electronic signal to a physical signal. Yeah. Okay, next. So then let me just introduce what we call, we'll go deeper when we are going deeper into the topics by topics within the control technique course. But let me just introduce open loop and closed loop control. Yeah, open loop control system is one in which the control action is independent of the output. So it means that the sensing mechanism is not there. It's not used, at least. Just like when we drive our car, and then you don't look at your speedometer, don't look at your dashboard. You just hit the gas and then just drive. So it means that you don't want to know, or you don't need to know how much speed that you are on at certain point. Yeah. So it's independent of that. You just hit that gas. Yeah. So there are two parts in here: controller and the control process or plan. So the controller is the person that hit the gas and then relate to some combustion engine or some acceleration in a vehicle, electrical vehicle, if it is using electrical vehicle, and so on. So there are two parts. Yeah. And then this is the graph, the block diagram for it. So the reference input, you just put something and whatever the controller is, and then going to the process plan and then the output. So it doesn't matter what is the output. We cannot do anything about it because we don't have any sensing mechanism, or we call as the feedback, to check that, or even to increase or to lower. We don't really have that sense. So example, a car speed control I just mentioned to you. Yeah. So just whatever the desired speed, you just hit the gas, and you don't know whether it is hitting that point or not. Just probably you feel that okay, but you don't know for sure how much is the speed. But for closed loop feedback is one which the control action is somehow dependent on the output. Why? Because it is fed back to the input, or I would say to the brain. So the brain somehow usually, let me put that. So the brain somehow can be, yeah, the brain usually is in here, from there to there. Yeah, this can be microcontroller, can be PC, can be PLC, whatever. Yeah, that's the brain. So when the controller hits the process in being inputted to the process or the plan will output something. Y is the output, and then this will be measured by the sensors here, and the sensors will be feeding the information to the brain. So the brain will calculate. For example, let me use this as a car control, yeah, with a feedback. So I want it to be 100 kilometers per hour. So I hit the gas, and then let's say me and the car is the total closed loop control system. So my eyes is looking at the speedometer, and then speedometer says is 90 kilometers per hour. So my sensor will tell my brain. So the brain will say speed up, yeah, accelerate, and then I hit the gas even more, and then check the speedometer again, the output, and by the speedometer, by the sensor, and then so on and so on until I get to my desired speed. Yeah. So just like your air conditioned AC system at home. Actually, when we set it to a certain desired temperature, let's say 20 degrees, what happens is the compressor will work, and then it will blow the cool air into the room, and the AC system already has a sensor also. It will sense the temperature of the room. So if you want it to be 20 degrees Celsius, and then the sensor sends it to be 25, then what it does is it will tell the chip, it will tell the brain within the AC system to keep doing the compressor activity and blowing the cool air into the room until it reach 20 degrees. That's why sometimes when you are setting your AC and then you turn it on, and it is like giving a noisy sound. And after some time, the noisy sound is just stop. What happened? It doesn't mean that the air condition is off, yeah. The blower is on, but is off. It's just the compressor activity, the one that giving the cooling action is stopped for a while because it is already reaching the desired temperature, like that. Yeah, that's the point of a feedback system. So the idea of feedback is to compare the actual result with the desired result. Yeah, so take action based on the differences. So if the difference is still big, then it will give the full force, like that. So when the action is getting slower, then it will be giving a slower force until no force should be given, no action should be given in terms of controlling output. Yeah, this seemingly simple idea, but is tremendously powerful. Yes, it is tremendously powerful. Feedback is a key idea in the discipline of control. So you can also apply this to management if you want to control how the system that you are doing at work. So you need feedback. How you are managing your people, you need feedback. Managing your finances, you need feedback. If you don't have any feedback for how much money in your account, then probably you cannot really spend as much as you like. You need to know what is the feedback, how many money coming in, how many money is going out, things like that. Yeah. Okay. So example, cruise control, yeah, car, yeah, like autopiloting, things like that. So you just set the temperature, set the speed, and it will should be going that way. If you have a cruise control like autopiloting, also like that. Yeah, autopilot. Yeah, I put the example here. So pilots sometimes just set it to be autopiloting, and then the pilot goes for a drink. Yeah, go for swimming if there's a swimming pool in the aeroplane. So the goal of control engineering design is to obtain the configuration, specification, and identification of the key parameters of a proposed system to meet the actual needs. So in this course, we will do a lot of modeling. Yeah. So basically, the main two is modeling and then control. So we specify, we identify the system, and then when we know the system, when we model, we know how it behaves, then we can control it. Just like people, when we get to know somebody, how we can actually work with this person, or quote unquote control this person, if we don't really know him or her very well. So this is about modeling. Yeah. So the first thing is establishing system goals. What do you want? If it is a car, what do you want to control? Is it velocity, acceleration? If it is robot arm, what do you want? What is your goals? Is it the speed? Is it the precision? Is it the what? Is it no fluctuation? So we must define our system goals and then identify the variables to control that. If it is about velocity, then we need to control the speed of the motor and establish the system configuration and identify the actuators and sensor. If it is a very slow moving robot arm, then we need to use what kind of motors, what kind of drivers, yeah, what kind of sensors for that. Does it have to be a very high force? Does it has to be a very high torque? Yeah. By defining that, then we can choose the right components. And then obtaining the model, of course. Yeah, I just mentioned it just now. Modeling is very important because when we know the model of the system, example, in this is later we'll study in S-plane or in Laplace form, and how we can actually model it and then find the response of it. And then, of course, after that, we design the controller. If you know the system behavior, then we can apply the controller. Before applying, of course, in the real thing, hands-on, then we could also do some simulation experimental tests. We can use the MATLAB or Scilab, Simulink or XCOS, some laboratory tests and all that, just to see how the response look like. And it is now we have an advanced simulation application, software that we can do. Even they come for free these days, freeware like Scilab or XCOS. Okay, so again, as I mentioned before, this is about system modeling and control. Let's look at the focus. Yeah, focus is first is mathematical foundation. We need to know how to model by studying first the mathematical foundation. So it is Laplace transformation. Laplace is based on complex variables, so it will use again your previous knowledge on complex variables, complex number. And Laplace transformation, we'll study this in this course, and then the properties, and then theorem, and then of course using the inverse Laplace form, and then we can use it to solve differential equation. Because when we come to system dynamics, there are this second dynamics, second topic, which is mechanical, electrical, or electromechanical system. When we want to model them, usually it will come to ordinary differential equations. Yeah, of course, this is for linear system. For non-linear system, we can use other method, which is state space, but it is not covered in this course. Yeah, and then transfer function. Transfer function is talking about the relationship between output and input. So and then we can because system can be consisting of many subsystems. So sometimes we want to connect every subsystem to another. Then we use block diagrams. Yeah, and then multiple inputs. Sometimes we don't desire, of course, noise or disturbance, but it just exists. It just exists. So multiple inputs actually is not the multiple input that we want, but it is created by the noise or disturbance, but we can handle it. We can study that later. And system response. Of course, as I said before, after the modeling, we can see the response of the system. So we can apply some input and watch the output of that. A first order system, second order system, and we also look at sinusoidal response of a system. Yeah, and finally, feedback control system, we look at open and closed loop system, like I mentioned before briefly, and we study the sensitivity, the disturbance, transient response, steady state error, and also the case study of speed control of a DC motor, and then the stability of linear feedback system, and finally the application of three-term PID, proportional, derivative, and integral control. So in this topic, we look at all of those. In this subject, we look at all those topics. So I hope that you can be prepared for that. So I guess that's all for the course introduction. Then we look at some more in details after this. Okay, see you again. Thank you.